A very good evening, respected professors, dear scholars, and students. Today, we are gathering here for the third installment of this online lecture series for the propagation of statistics education and research, which has been conducted by Calcutta Statistical Association. The primary objective of this series is to educate and engage the undergraduate students, postgraduate students, and doctoral students for specializing in statistics and related disciplines. Eminent statisticians from India and overseas have previously delivered lectures garnering positive responses from students and researchers. The previous sessions are already available in the CSO website. Today, we are honored to have Dr. Dootika Vats, Associate Professor from Department of Mathematics and Statistics at IIT Kanpur, as today's speaker. The title of our talk is A Gentle Introduction to Markov Chain Monte Carlo. The session is anticipated to run for approximately 1 hour and then followed by a 10 to 15 minute interactive discussion. Now I am going to introducing Dr. Vats with some little bit bio of her. Dr. Vats was an NSF postdoctoral fellow with Professor Gareth Roberts at University of Warwick. Her PhD was from University of Minnesota under the supervision of Professor Galen Jones. Research interests of Dr. Vats are Markov chain Monte Carlo, output analysis for stochastic simulation, and stochastic optimization algorithms. Dr. Vats serves as an associate editor for Journal of Computational and Graphical Statistics and the Sankha B. Dr. Vats is now associated with Indian Academy of Science too. She has delivered various lectures in India and abroad. Now I am requesting Dr. Vats to deliver your lecture. Madam.
Yes, sure, absolutely. So I hope I'm audible, and I'm just going to try and share my screen now. So one problem I usually have with Google is perfect. Don't show this. Is that I actually once I start sharing, I cannot see my audience at all. So please, if you have any questions, feel free to unmute yourself and shout at me and just ask the question, because I'm not able to really see the audience or see somebody waving. Can somebody confirm kindly whether the slides are visible and I'm audible properly?
No, you are audible, madam, but the sides are not visible.
No, sides are visible. Yes, sides are visible. I think somewhere you have some problem.
Maybe it's Thank you.
Okay, and also, can we confirm slides are changing as well? So
yes,
yeah?
yes, it is fine.
Okay, perfect. Okay. Okay, well, first off, let me just start by saying it's an absolute honor and such a wonderful opportunity to speak to the members of the Calcutta Statistical Association. I see and I've been told that there's a lot of young people, a lot of undergrads and masters and PhD students. So I have chosen a topic that is a little bit more pedagogical. I'm not talking about new research areas, etc., because the area I work in is not usually taught in the classroom, at least until BSc, definitely not taught in a typical classroom. If at all, you might learn it in a master's program and a PhD program, but not in an undergraduate classroom, which means it becomes difficult to talk about research to undergraduates on this topic. Nonetheless, so what I've pivoted to is giving a more introduction to the general area I work in, which is Markov chain Monte Carlo, very useful sets of algorithms. So I hope the rules are clear. If you have a question, just feel free to unmute and shout at me, no problem. Okay, so we start very quickly. So what am I going to be talking about? I am going to be talking about the problem of sampling in this talk. Now, most students, especially younger students, when you hear of sampling, you think of sample surveys, sampling observations, data in the real world, but I'm not talking about that kind of sampling. I'm talking about computational sampling. And okay, so I'll describe what this is, but the fundamental problem that we are focusing on is computational sampling, or sampling as we call it. What is this problem? So consider, for example, a standard Gaussian distribution. So Gaussian meaning standard normal distribution. And I denote this by normal 0, 1. Okay? Now, sampling from normal 0, 1 implies that we have what we call realizations of random variables, x1, x2, x3, x, and so on, such that each xi has a distribution normal 0, 1. And I'm being very careful with the words I'm choosing. I'm saying that we have realization of random variables. These capital X's are the random variables, and my realizations are typically denoted by, let's say, small x's, etc. Okay. So what I mean is I have actual samples from normal 0, 1, x1 up to xn. And we know from fundamental courses that the notation we follow in statistics is that each xi follows normal 0, 1. Now, on purpose, I didn't put IID here. Why? Because I'm going to talk about it. So what I'm saying is, ideally, we want independent and identically distributed samples, IID, which means that xi and xj are independent from each other. I is not equal to j. And both and all are drawn from the same exact distribution, which means they're IID. Okay, this is, a standard sampling issue. I have a distribution. I want to get IID samples from that distribution. So let's take a look. What do I mean? So I know I want to do IID sampling from normal 0, 1. And this has a density function 1 by square root 2 pi e to the power minus x squared by 2. And what I've done over here is, oops. Okay. Yeah, sorry. What I've done over here is I've plotted the density function. Okay. So x on the x-axis, density function, and the y-axis. And what I'm going to do now is I'm just going to draw samples from the standard Gaussian distribution. And so when I draw one sample, I will click and a new sample will appear. It came right about here. This is a green dot that says, well, that's one sample from this distribution. I click again, and now it's this green dot, and it's x3. That's the third sample from the distribution. This is x4, another sample from the distribution. And I can keep doing this and basically keep getting tons of samples when I might have a lot of samples that are actually, why are they from normal distribution? Because a lot of them are from the middle, because that's where the PDF takes a, that's where the PDF takes a very high value. And then the PDF takes lower values, means the weights are lower. And so here, I'm going to expect lower number of samples. And once I have all of those samples, I can assemble them in what I call an approximate density function to see that what is the approximate density from these samples. And I get that the approximate density looks something like this blue curve from these samples. Now, this is only 1,000 draws from normal 0, 1. So the blue curve doesn't exactly look like the black curve, but that's okay because this is an estimated density, the blue curve, from my finite number of samples. If I were to let this sampling go on till infinity and I get large number of samples, then this blue curve will exactly match my normal curve. So what you should note is that I'm talking about samples obtained on a computer, okay? I just got these samples from a computer following a certain distribution. And this is why it's computational sampling. So how does the computer actually sample? So as you can imagine, there is a whole process and system of training a computer to sample from a given target distribution. And I've written this in blue because this is a technical word. I have a distribution that from which I want to get a sample, and that becomes my target distribution. And to actually implement this sampling strategy, this requires what we call an algorithm to be able to say, hey, do these 4-5 steps, and that will give me a sample from this distribution. And this whole area of research and implementation in statistics is called computational sampling, or even Monte Carlo. Okay, so let's take a look at a slightly different example. We're going to take a look. We're going to change the desired target distribution. So the desired target before was a standard Gaussian distribution, and now we're going to look at a different target. So the target, my goal is to do uniform sampling from a circle, or rather a disk actually. So consider a uniform distribution over a unit disk that's centered at the origin. And the way I'm going to do my sampling from this uniform distribution over the disk is we're going to define a box that contains the disk. Okay, so there's going to be a box we will create that's going to contain the disk, and we will obtain samples from the box. Now, obtaining samples from the box is easy because I can obtain sample on the x-axis of the box randomly and on the y-axis of the box randomly, and together they give me a joint draw from the box. Right? So I just join the tuples, and that gives me a joint draw from the box. So let's actually see a visualization of this. Okay, so let me pause here just to say what's happening. So this is my circle. That's a unit disk circle. And I want to get samples uniformly distributed over this disk. What I do is with this thick black lines, I've enclosed the circle perfectly in a box. Okay, and what I'm going to do now is I'm going to draw randomly from the box. Okay, so the first draw I got is this blue draw that's randomly drawn from the box. Now, because this draw is inside my circle, also it's inside the box for sure, but it is inside the circle, I say, okay, this looks like a good draw because it's inside the circle, so I accept the draw, which is why it's in blue. Okay, I draw another point, and it's right on the corner here, but it's in the corner, but it's inside the circle, so I accept the draw still. So this is in blue, so it's accepted. This third draw over here is also from within the circle, so I accept the draw, and I keep doing it. But now you see, I from the box I propose this draw. This draw is indeed from the box, but not from the circle. And so I say, no, I don't like that. This cannot be a draw from my circle, and so this is a bad draw. I will reject this draw. Please remove it. So I have colored it in red, as in I will remove this. And so I'm just going to let this run randomly for a while, and I will just keep this running. Okay, and there'll be a mixture of red and blue, and eventually, if I run this for a long time, I will see a ton of blue dots, which are all inside the circle, and a ton of yellow dots, which are all outside the circle. All the yellow dots are rejected as not being draws from inside the circle, and all the blue dots are all draws from inside the circle, uniformly distributed over the disk. So this is one strategy to actually sample uniformly from a disk. Okay, so this is one sampling methodology, for example. Okay. And this particular methodology is an example of an accept-reject sampler. And so we'll talk a little bit about accept-reject samplers later as well. Okay, so why is it called accept-reject? Well, because I'm proposing a move from the box, and I'm either accepting it, which is blue, or rejecting it, which is red. And so an algorithm is effective if it has a high probability of acceptance, right? If I had chosen a much bigger box, then that would have maybe led to a lot more rejections. And so an algorithm will be effective if it has a high probability of acceptance, at least in this case. Okay. So what is the probability of acceptance for this previous algorithm? We note that the rate of acceptance of the points proposed was actually fairly high. What I mean by that is that it does look like that the proportion of blue dots is much larger than the proportion of the red dots, right? Which means we are more often accepting than rejecting. So what is it mathematically? Well, the probability of accepting turns out to then just be, well, what is the comparative area of the circle divided by the whole area of the box? That's the probability of accepting. The area of circle divided by the area of the box, well, the area of the circle is what is it? Area is pi r squared, and radius is 1, so it's just pi. And the area of the box, it has to encapsulate the circle, so each side is 2 units, and so the whole area is 4, 2 squared 4. So we have pi over 4, which is 0.78, which means that 78% of the draws from the box are accepted by the algorithm, which is pretty good, which means only roughly 1 out of 4 draws is wasted. But what if I change the problem a little bit and I say, well, let's repeat this for p balls in p cubes to sample from a p-dimensional ball. Okay, so instead of a 2-dimensional ball, which is a disk, I sample from a 20, 15,000 dimensional ball. Like that's, I can't visualize it, but that's my goal. I can use the same methodology. If it's a sphere, I can encapsulate the sphere in a 3-dimensional cube, right? And as long as I can sample from the cube, I can still do the accept reject algorithm. And I can repeat this idea in p dimensions. So then the probability of accepting in the general p dimensions turns out to be, with the same logic, the volume of the p ball, the p-dimensional ball, divided by the volume of the p-dimensional cube, which I will not let you do mental maths, which just basically turns out to be this, where this over here is the what is called the gamma function. And if I can put in a value of p, I can do a quick calculation on the computer. And this tells me that, let's say I want to sample from a 15-dimensional ball using a 15-dimensional cube as my enclosing box. Well, then my probability of acceptance is 0.0000116, which roughly means that it will take me 1 lakh draws from the box to actually get 1 acceptance from the p-dimensional ball. And that's just 1 acceptance. Now, if I want 1,000 samples or 100 samples from the p-dimensional ball, then I have to do this 100 or 1,000 times, and that becomes extremely, extremely inefficient. Okay, so this is a classic example of geometric progression or exponential increase. Okay, so then the question is, naturally, can we do something that's more efficient than enclosing a whole box, putting the whole ball inside a box? And here's something more efficient. What I'm going to do, so that I'm going to identify that the reason that this sampling strategy is not effective in high dimensions is because in high dimensions, the volume of the ball is much smaller than the volume of the cube. Because it is much smaller, I'm basically throwing some darts in a dark room and hoping that I hit a very small corner in the room. Okay, it's a very small corner. I have no information, and I'm just throwing some darts, and most of them will be misses. Right? I will not get a good hit most of the time. Unless I do the following, where I say, okay, let me just choose one small dot on this disk, or one small dot on my mark in this dark room, and then I will just look around this dark room. So what I mean by that, let me come back to the circle, is this is my circle. And instead of enclosing the whole circle in a box, I say, okay, I choose one point in the circle. It could be any point as long as it's in the circle. And then I say, you know what? I don't want to guess randomly. I'm just going to look in a very small box around this point. And the logic being, if this point is in the circle, then it is likely that points close to this are also in the circle. So I don't have to randomly guess, because that's very wasteful. I can just sort of look around me and get a new point based on that strategy. So the way this works, and this is a classic example of an MCMC / Markov Monte Carlo algorithm, is given this point, I create a new box with this point as the center, and I draw uniformly within this box now, smaller box. And I see that, wait, this is the point I draw. It is in the circle. So I say, okay, this is a good point. And in the next iteration, I actually move the box to this blue dot, like this. I move the box to this blue dot, to the center, and then draw a new point, which is this blue point, from this box. And that also is in the circle. So I repeat this whole process again. And then I repeat it again, and I repeat it again, and I repeat it again. And all of these points are in the circle, so I keep repeating it until, and it's going to happen soon, there we go. Until I see that, okay, I was here this is the center of a box. This is my current iteration. And I see that this point, red point, is now outside the circle. Now, outside the circle, I can't sample. And so what I do is I reject this point and I say, okay, I reject it. And actually, I stay where I am. Okay, I'm going to stay exactly where I am, which means I draw a new proposal, a new point from exactly where I am. So notice, I'm just going to click very quickly now. Notice that the box will not move. So I do this. The box didn't move, but I did get a new point. Got a new point which is inside the circle, and then I keep moving this. Again, this point is outside. I get a new point with the same box, and I keep doing this, right? And I'm just now going to let it run. And what you see is that these are not random samples anywhere. These are all close to each other and currently only exploring one part of this space, right? But let it run for a little bit. I'll let it run for a little bit. And finally, after some iterations, I see that I have actually gotten samples all over my circle, and a few samples are proposed outside the circle, but they cannot be proposed so far away. So the wastage that's happening when I'm sampling from these corners is no longer there, right? They're only a little bit farther outside, and it's a lot more efficient. Okay. Great. So what is that? What was that algorithm? That is an example of what we call a Markov chain Monte Carlo algorithm. So let's now start defining this algorithm and this concept properly. So I'm going to now denote any distribution that I want to sample from as my target distribution. And I say, let capital F be my target distribution. So capital F denotes my target distribution. And it is defined on a space which has the support is script X. I call this script X. And the goal is to sample from this distribution. So F was the standard normal in one example, and F was this uniform distribution over a disk in another example. So what do we do in MCMC, in Markov chain Monte Carlo? Well, we construct a Markov chain such that F, the target distribution, is the stationary distribution of the Markov chain. Now, those of you who've had courses in stochastic processes before will have to be a little cautious because a lot of your intuition will not translate into this. The reason is for two reasons. One, in typical applications of stochastic processes, we are given the Markov chain and we want to analyze the stationary distribution, the invariant distribution, the limiting distribution. We want to understand what that is. In Markov chain Monte Carlo, it's what we call ulta. It's the reverse. We are given a distribution and we want to build an algorithm that defines a Markov chain that has this distribution as the stationary distribution. So the thought process is a little reversed. And the second difference is that most of the coursework that happens in introductory stochastic processes courses defines on a discrete state space, which means I have discrete states. I'm jumping from a state I to a state J, and then to a state K, and so on. However, if I think of the Gaussian distribution or the uniform distribution example, these are continuous distributions. Right? I want to, my Markov chains are defining continuous random variables. So I can no longer think of jumping from one state to another. I have to think of jumping from a state to a set. And that is why the Markov chain is not defined by a transition matrix anymore, but rather what we call a Markov chain transition kernel. And how is the kernel defined? Well, take a point in your space, script X, that's one point, and take a set A, which is a nice set. So this is in the Borel sigma algebra. It's a nice set, basically. And the transition kernel is Bx comma A. What is that? It's nothing but the probability that given xk at any iteration k is equal to x. So given I'm at a current state x, what is the probability that the next state will go into the set A? Okay, because I can no longer measure probability of individual states, but I can measure probability of sets, just like any continuous random variables. So this is what the Markov chain is defined by the transition kernel. The key to MCMC algorithms to get nice samples from distributions F is to construct good kernels P. So if I can construct good kernels P that are efficient, take less time, and converge very quickly in terms of its Markov chains, that's a good kernel. Okay, so let's look at one particular algorithm that actually is able to do the following. So what seems very strange is that F is given to us, and now we have to build a Markov chain that targets F, that has F as its stationary distribution. This seems quite daunting, but there's an algorithm that is able to do this for us quite easily. This is called the Metropolis-Hastings sampler or Metropolis-Hastings algorithm. So let small f be the density of capital F, right? So the capital F is the distribution, small f is the density. And we're going to choose a kernel qx comma dot, and this has density qx comma. All this is a conditional distribution. So qx comma dot is just the density of a conditional distribution. And to simplify things, I'm going to assume qx comma y is symmetric, so that x comma y is equal to q y comma x. And if this is not very clear, we'll see again an animation for this. So what I'm going to do is, given that I'm at a current iteration xt, I will obtain my next iteration in the following way. I get y, which is what I call a proposed value, from my distribution. So this could, for example, in the previous example, this was the square. Q was the square around my current point, square centered at xt. And what I do is I calculate alpha, which is the minimum of 1 comma, the ratio of the density function evaluated at y divided by the density function evaluated at xt, my current iteration. And I say that I will set my next instance xt plus 1 to y with an alpha probability, and which means I will accept this move with an alpha probability, and I will reject it, which means I'll stay exactly where I am. Xt plus 1 is xt with probability 1 minus alpha. So what does this look like? This algorithm seems a little contrived, but let's just see what this algorithm looks like. I'll go back to the Gaussian example case. Okay. So this is my target distribution, my Gaussian target distribution. So F is normal 0, 1, and Q is normal x comma 4. Okay, so Qx is normal x comma 4. Whatever x is, whatever is the current iteration of the Markov chain, that will be the mean of the normal distribution. So my current iteration is this green dot over here. I'm going to draw the density of Q based on this current iteration, and that is this density. Here, notice that it has a larger variance than a standard Gaussian. This is my density. I'm going to propose from this density. I propose this green value. So currently, this is my y. Okay. Now I want to decide whether I accept it or reject it. Now, based on the ratio, it's going to calculate and it's going to randomly decide whether it wants to accept or reject it. So it turns out it's a green, it doesn't want to accept it based on that acceptance ratio. It says, no, I don't want to accept it. So I reject it and I stay where I am. So the next time I draw from that exact same proposal, and it proposes that value, rejects it again. It says, okay, let's draw another. From the same proposal, I'm going to draw another value, proposes that again, and rejects it again. And it proposes that value, which is in such a low area of probability, it doesn't want, it doesn't look like a good value. So it is rejected again. Okay. This value, on the other hand, is in a very high area of probability according to F. Okay. And that gets rejected. See, it's turned into green, so that gets accepted. Sorry. Okay. And I can keep doing this. And I can keep doing this. I'm just going to let this simulation run. That it's going to keep going and getting samples. And now you can see that it's moving a little bit. Of course, it rejects a few, but it is moving a little bit. And this is finally, after a certain number of iterations, we see something similar to what we saw in the random sampling, RID sampling case, where what we saw is that most of the samples are over here, and we get some samples outside, and the estimated density function like this doesn't look that bad. It looks like actually my density is exactly or very close to the actual blue density curve. So despite these being not random IID samples, we are able to get something. We're able to draw samples from the Gaussian distribution. Now, I will say that these are all toy examples I'm giving you because more complicated ones are difficult to understand. We don't need a sophisticated algorithm like this to draw samples from the normal distribution for sure. But this is just to indicate. Okay, so what's really going on mathematically? So let's assume that the initial value x1 follows f1, some distribution f1. So the first draw that I have, I draw randomly from f1. And this f1 distribution is potentially different from f. F is our target. It doesn't need to be f. Okay. I'm sorry, is there a question? Okay, let me just.
Yeah, there is a question, but you may continue, madam. Then after that, after your talk, then we can discuss. Yeah,
Okay,
it will be
sure.
better.
Okay, sure. Thank you. So the density of f1 is small f1, let's say. Then what am I doing? Well, I want to find the marginal distribution of x2, and that I denote by f2. Okay. So how do I find the marginal distribution of f2? Well, the distribution f2 for a set A, measured for a set A, is nothing but you write down the joint distribution of x1 and x2 and integrate out x1. But the joint distribution is nothing but the marginal distribution of x1 and the conditional distribution of x2 given x1, which is exactly my Markov chain transition kernel distribution. And once I integrated out f1 as in x1, the first iteration, I just get f2a. Now f2 may not be equal to f. Now remember, I want to draw samples from f. So I start from some f1 distribution, and then after one step of the Markov chain, I'm getting to a distribution f2 and so on. Okay, so I'm not very happy with what's happening here. I want samples from f. Okay. In general, the marginal distribution of each of the draws, ft, may actually not be equal to f. And this may not be good news, right? The marginal distribution at time t is ft, that may not be equal to f. But this is when x1 started from f1, which was potentially not equal to f. What happens when f1 is f? So let's see. This is exactly the definition of stationarity. And so one can show that the transition kernel P of the above MH algorithm satisfies the key property of stationarity, which is that if I start from F itself, this is the marginal distribution of x1, then look at the conditional distribution of x2 given x1, integrate out x1, then that is nothing but F. This is F over here and F over here. So that becomes a stationary distribution. And what this says is if we start from F, then every step of the Markov chain will still yield a draw from F. Okay, which seems a lot more promising that at least I will keep getting a draw from F. Okay, so this property ensures that if we start from one representative draw from F and run the sampler, then we will continue. X1 is from F, then X2 is from F, and Xn is from F. For those of you wondering, these are not independent draws at all. It is a Markov chain, so these are correlated draws, and I will get to that later. Okay, they're not independent. Okay, but let's visualize what's going on. Now, for the next couple of slides, I want you to think of this purely as a visualization exercise. This is typically not how people run MCMC algorithms. But the idea is that if I want to understand the marginal distribution of a random variable at any time point, then I need multiple copies of that random variable, right? so that I can understand, okay, I have 100 copies of that random variable. Now I can visualize its distribution, right? To visualize. So here's what I will do. We will repeat the MH algorithm some capital R number of times so that I will draw X1 soup 1 from F. So I'm starting the first Markov chain from F. X2 is the second iteration of the first Markov chain, the third iteration of the first Markov chain until the nth iteration of the first Markov chain. So every row is a Markov chain, but I will run R such Markov chains. Okay. Then what I will do is I will just look at one column of this Markov chain of all of these Markov chains at different time steps. So if I gather all my starting samples, these are just R independent copies from F, just all of these samples. And then if I draw all of these samples, these are just capital R independent copies of the marginal distribution F2, right? And then these are all, after that, these are all independent copies of the marginal distribution at F time N. This is what we will visualize. Just to understand what's going on with the distribution that is imbued by the Markov chain. So what I do is I start exactly from F, right? And so I have IID sample from standard to normal, and these are all my starting distribution from F. Now each of these runs its own Markov chain, and I run all of those Markov chains for one time unit. Okay, and that is F2. And I see, okay, this is my F2, also looks fairly close, a little off here. But remember, this is estimated density, not exact density. And I will run for F3. F3 looks also very close. F4 also, and all of these look very close, and I can keep running. And all at time N, time 20, 25, 30, 40, 50, the distribution of the random variables looks exactly like my target distribution, right? Subject to variability. So this is great. This is a visualization of stationarity that I'm starting from F, and the distribution of these random variables continues to be F. Great. But here is an issue that if we could sample from F, then why would we do all of this? Right? We are doing all of this because I have made the case that we cannot sample from F, or it is very, very expensive to sample from F. So it is often impossible to draw even one draw from F. Thus, we know factually Ft is not equal to F for any t. What does that mean? The marginal distribution of the Markov chain at time t is not equal to our desired distribution. But is it close? And what we know is that the Metropolis-Hastings algorithm and many other algorithms, when carefully designed, can be done in such a way that the algorithm is what you call F-ergodic. What does that mean? It means that as time goes to infinity, then for any starting distribution F1, give me any starting distribution for the Markov chain, and let's study the distribution at time t, which is Ft, and its difference from the target distribution F. And let's measure that in some appropriate distance. I don't want to go into technical math here, but let's measure that in some appropriate distance, how far Ft is from F. Well, that distance goes to 0 as t goes to infinity. What that means is that as you keep running the Markov chain for longer and longer, I'm going to get my samples approximately from F. Okay, so we are going to try and visualize this. But we should remember that eventually they will be from F, but in any in any finite time, they will just be close enough to F, not exactly F. Okay. And I will repeat the same process as I described before, but now I will set, instead of the starting distribution to be F, I will set it to be F1, which is a very bad starting distribution, gives a point mass at -1, which means all my starting draws for all the R Markov chains is -1, -1, -1, and each of the rows again is one Markov chain. So I'll run each of the rows again. Okay. So now this is my visualization. At time 1, this is a point mass at 1, so it's a high peak at 1. At F2, what is the distribution of F2? I see now that there's a little bit of push. At time 2, there's a push away from the point mass distribution. It's still not the black curve at all, but it's a little bit closer. And F3 is a little bit closer, F4 is a little bit closer, F5 even more. And by the time we get to F6, which is time point 6, I see that FT, F6 and F are very close to each other, as close as the random sampling was. Okay. And now I can just keep running this, and I see actually by the time we get to F20, F30, this is practically indistinguishable. In the beginning, I have certain bias, and then eventually it sort of goes away within 10, 15 steps of the Markov chain. This is a way to visualize ergodicity. Okay. Oops, sorry. And I'm repeating the same thing over here, where F1 is the normal 4, 0.01 distribution, which means that it is a point mass at, not point mass, but a very small value at 4. Very small variance at 4. And then F2, this is what the distribution turns out to be. F3, this is what, so I can see it move. And now it slowly starts coming back, almost like magic, starts coming back to F, right? And that's exactly what happens. So in the beginning, it's very far away, and then slowly it starts coming back. And it happens within 10 to 20 to 50 steps. Very, very quickly. So now let's come to the question that's probably will keep you up at night, that are these samples any useful? If we get samples close enough to F, and maybe we're okay with that, a critical issue is that these are correlated samples. Now, a lot of our fundamental courses in BSc, MSc, and even PhD start with the following sentence: let X1 up to Xn be an IID sample from distribution blah. And so a lot of our fundamental theory and concepts are established for IID samples, particularly independent samples. And so this seems like this should not be allowed. But the issue is, when you can't do IID sampling and literally can't do it, then you must do something else. And so we do correlated sampling. So are they any good? What can we do with the samples? Okay, turns out if the Markov chain is F ergodic, which means that the marginal distribution converges to F, we can do a lot. There's a lot of things we can do with the samples. For example, if we are interested in the mean of the distribution F, so expectation of X for where X follows F, and let's say I denote the theta as this mean, so it's nothing but this integral over here. And let's say this is what I want to estimate. What I do is I can go to the computer, run a Markov chain, okay, that has capital F as my as the target distribution, take a sample average, which is X bar n, so which is just the sample average. And because the Markov chain is F ergodic, there is a law of large numbers that holds for this particular Markov chain. So as n tends to infinity, X bar n will converge to theta. Okay. So even though we have bad samples from the target distribution, and they're truly bad, they are not independent and they're approximate, you still have a lot of the fundamental paradigm of statistics still holding. Okay, so let's actually visualize this. So what I do is, for my Gaussian distribution, each of these curves in colors you see is one run of a Markov chain. So these are 20 different Markov chains, and I started them from various different points. Now what I'm plotting is actually the running estimated mean. It means I run my Markov chain for overall 5,000 steps, and at every subsequent step, I calculate the mean of the samples we have so far. So at this point, these are all the sample means of the Markov chains that have been accumulated for 1,000 steps. And then again, this is the sample mean at 2,000. And we see that as this is going, as I keep increasing my sample size, all of these are converging to 0, which is the mean of a standard normal distribution. Right? The means are all converging. Again, this is a visualization of the law of large numbers. Of course, this is not a proof, just a visualization to help us understand. What about variability? As a statistician, I am not happy with just estimating theta. I can always estimate a parameter and say the value is 1. Okay, nobody can question me. It's my guess. You come up with a very fancy estimator. that has certain value, great. I just say it's 1 without any information. Both of these are estimators. Now, obviously, your estimator is actually probably better than my estimator for many reasons. So variability is something that I need to have, I need to assess. And so, I need to know whether my estimator is bad or not. In IIT sampling, we often do this via a central limit theorem. And in addition to variability, we get asymptotic behavior in terms of distribution. So what about a central limit theorem here? Can that hold? Well, yes. There are additional conditions and we have to be careful. There's a lot of Markov chain theory involved. But we may have a central limit theorem that yields that as n tends to infinity, my sample mean with appropriate scaling converges to a normal distribution with mean 0 variance sigma square. I will talk about this variance in a second, but it is a little complicated. But a CLT holds. CLT can hold under these conditions. So can I visualize a CLT? Well, I know that this implies that x bar n approximately follows a normal distribution with mean 0 and variance sigma squared by n. So for each of those 20 Markov chains that or R Markov chains that I had before, I'm going to plot a histogram of x bar t at different values of n. So this is at n equals 100. So that's not very large. This is at n equals 200, little better. And I can keep going, keep increasing. And I see now it's starting to look Gaussian-like. Okay? And obviously the variance is sigma squared by n. So the variance is also now reducing. So I let it run. And now I can see that the variance is also reducing by a factor of 1 by n. Okay? And I see the CLT behavior also kicking in. So I can see that there is a central limit theorem. And there is a structure to how variable these estimators are as well. But what is the variance over here? How do I know what the variance is going to be? So because the samples are correlated, variances are tricky. And that's because variance of x bar, which is this sample average, is not equal to the sum of the variances, which is something I get when I have independent samples. Because I can't pull the summation outside, that the variance of sum is the sum of the variance. It's not something I can do. It becomes a lot more complicated, okay? And that's also because there is all sorts of pairwise and serial correlation in my Markov chain. So I need to be able to really understand and assess that. And that's actually one of the areas that I work in terms of my research is what does this variance look like and how can I estimate that variance? So this is typically something people start with is where is MCMC used, but I'm ending with it. So who uses MCMC? Why are people interested in drawing samples from a distribution on a computer? Well, traditionally, typically, not always, and now there's a lot more uses, the main use is in Bayesian statistics, where somebody has built a model which has led to what is called a posterior distribution, which is typically quite high dimensional. And I have a distribution F whose density is small f that is proportional to F tilde x. We know F tilde x. We don't know the proportionality constant. And also this is in high dimensions. Now, this is a model we have built and everything relies on this F. And I need to know its mean, its quantiles, its mode, its variances, etc. And I can't do it because I don't know this, don't know the normalizing constant, and it's a very complicated form. This is where Bayesian statistics relies on us people who work in MCMC to say, can you please solve this problem for us? By drawing samples from this on a computer and saying, okay, now using those samples, I can guess what the mean of F is. I can guess what the quantiles are. I can guess what the variances are, and so on. Where are these Bayesian models used? In almost all facets of science. So there's a high usage of Bayesian model in astrophysics in an area called astrostatistics. In genetics, a lot of genome sequencing models, very big Bayesian economics models, ecology models. In modern ML AI, the Bayesian models are also essentially a form of probabilistic generative models. There's also language models. So I've had students who've worked on the use of MCMC sampling for LLMs and language models. And anywhere where you want a high dimensional integral solved and you can't solve it, one can use MCMC. Okay. What does research in MCMC look like? Well, For example, a great question to think about is how large should be the width of the box in my MCMC sampling scheme from the sampling from the uniform disk. I chose a particular width of the box. How did I choose that? Can I make it larger? Can I make it smaller? What happens when I make it larger or smaller? Is there an optimal width of the box? These are questions that are actually very pertinent to research in MCMC. But is a box a good proposal? What about an ellipsoid? Can I use maybe some other type of structure? And how do I assess what is a good shape or a good proposal and what is a bad proposal? What about theory? Well, what is the rate of convergence of the Markov chain? So you have a Markov chain, and I know that it doesn't quite get samples from F, but based on different problems, it converges to F either very quickly or not so quickly. Can I characterize mathematically the rate of convergence of the algorithm? And how does it affect a practitioner in astrophysics who's trying to understand these problems? And a very important question is, how good are my estimates? When should I finish terminating the Markov chain? In real life data, we go out and do a survey, and based on the number of people that are willing to answer our survey, our sample size can be decided. However, these are samples on a computer. Now my samples will keep on coming until I decide to say end my sampling procedure. When should I end it? We can't wait forever. We must come up with a technique to end it. So I will end now with just to say that unfortunately there are not many good introductory books on MCMC that find a balance between theory and practice. A good reference to understand where MCMC is used and what it is made up of is the Handbook of Markov Chain Monte Carlo by Brooks et al. So this is a pretty good book, I would say. Okay, that's all I have. I'm very happy to take questions. I just want to say, because I think mostly talking to students here, we at IIT Kanpur, we have a Department of Mathematics and Statistics, and we are a reasonably large number of faculty in statistics, and we run 3 full-fledged statistics programs. The first is a BS MS in Statistics and Data Science that is through JEE. I'm guessing none of you are high school students, so that may not be very interesting to you. But we have a very popular and very sought after MSc program, admission for which is through JAM. It's a historical program. It's been running for many years, and we get some really good students, and we would really love to continue getting students for that as well. Similarly, for our PhD program, the entrance is through your regular GATE and JRF. But if you're interested in any of these opportunities, feel free to send me an email. Email is there, and I'm very happy also to take questions.
Thank you, madam, for your nice presentation.
Thank you.
Now, I'm requesting the audience to make some questions. Yeah, there are some questions. Please go ahead.
There was one in the chat box. I just want to see. Are the samples independent? Okay, I think that's been answered. Yeah, hopefully they're not independent, and that is a practical issue. But a lot of our machinery that we believe exists only for IID setup actually can exist for correlated setup. It's just a lot more technically intensive to study that. But as I've discussed, a lot of the things still hold despite the correlated samples issue.
Good evening, ma'am.
Good evening.
This is Dr. Dharmendra from Chhattisgarh, Bhilai.
Okay, hello.
Okay, right. My question is whether any application in MBA that Markov chain in management.
MBA I mean, yes, certainly. So, for example, econometrics is a so if I look at econometrics and finance management with a finance focus, there's a large number of Bayesian models that analyze many. You can even look at like marketing trends. You can look at financial trends, and there's a lot of Bayesian models. Now, once you have a Bayesian model, which sort of says, which is built to answer these questions, it is typically going to have a posterior distribution that is not available to us. And there you will have to then use something called Markov, like what I talked about, Markov chain Monte Carlo. So,
Okay.
I mean, there is no limitation of applications. Anywhere you find Bayesian models, MCMC exists.
Okay, ma'am. Thank you very much.
Of course. There's a question up by Aprajita. So consider two Markov chains very well, A and B, targeting the same distribution. Chain A has a high acceptance rate, 0.9, but slow mixing, and chain B has a low acceptance rate, 0.1, but fast mixing. Which chain is more desirable? This sounds like a very like a quiz style question for me. So actually, the first thing I will highlight is acceptance rates. Depending on how they're constructed, actually can sometimes tell you whether something is going to be slow or high mixing. So, for example, I'm quite fascinated to know that the chain has low acceptance rate but fast mixing, because that's very, very rare for a chain to have very low acceptance rates but have fast mixing. It's possible, but very, very low. So actually, high acceptance is typically not what we are after in MCMC. And the reason we are not after it, maybe I'll go through, I'll explain this via a particular slide. So what's going to happen, unfortunately, I didn't show this concept. What's going to happen if I want a really, really high acceptance rate? For example, this proposal that I've chosen gives me a relatively low acceptance rate, which you can see because a lot of these first few samples are rejected, which means the acceptance rate is not good. But to get a high acceptance rate, I can squish my my proposal to be a very thin proposal, so I can make the variance like 0.1 or 0.01, and then it's going to only propose value close to where I am. And because proposing values close to where I am can give me can tell me that okay, then this is a nice area already. I'm willing to be around this area, so that will lead to high acceptance probabilities. However, what will happen is that the amount of correlation in my Markov chain will be very, very large. So if something has a high acceptance rate, it's likely it will have slow mixing. There are certain cases when that's not true. So, but high acceptance rate by itself is not something that is desirable because it will typically have slow mixing. So anything that has fast mixing, and by mixing, for those of you who are not familiar with this, mixing just means how fast is my Markov chain converging to the true distribution. So for those that anything that has faster mixing is the better Markov chain, assuming it takes the same wall time. So you know, this is also a very natural thing that these are all happening on a computer. They take time sometimes, and so if one is very slow in terms of time, maybe I don't want it. So if time is not an issue, always faster mixing chain that converges faster to the target distribution is the way to go. Okay. Hopefully that helped.
Thank you, ma'am.
You're welcome, Aprajita. Anyone else? Any questions I can help answer?
Yes, ma'am. There's some question in chat box from Atre.
Yes. Atre, yes. If your target distribution is normal, then is it necessary to start with normal in the Markov chain? So first of all, if your target distribution is normal, you don't need to use MCMC, right? Not at all. But for the thought exercise, if your target distribution is normal, no, still absolutely not. You can start from any distribution. So for example, here I started from the following distribution. F1 was a point mass distribution at -1, not the normal distribution. So it was a point mass distribution at -1. So I'm starting from that distribution. And despite me starting from that distribution, very, very quickly, I converged to the Gaussian distribution within 10 steps. Okay. Or converged, visibly converged. Obviously, it's never exactly converged, but very, very quickly, I was able to move very close to the target distribution. So no, as long as we are using an ergodic Markov chain, we don't have to do that.
Yeah. Thank you, madam. Anyone else? Again,
yes, due to ergodicity, we are assured of the convergence. Yes, absolutely, exactly. That is what ergodicity basically means. So I will go one slide back. So ergodicity basically means that the distance between ft and f is going to 0 as c goes to infinity. When is a Markov chain f ergodic? I didn't talk about this. When it is, so if you know Markov chain theory, when it is f irreducible, aperiodic, and Harris recurrent. I didn't want to talk about like very core Markov chain theory, so I didn't go into it. But yes, f ergodic means that it will converge to f as c goes to infinity. Could you please throw some light on how we can use MCMC in missing value imputation? Sure. So one way to do this, and I'm not an expert in missing values at all, but so what is MCMC? MCMC is basically a way to estimate this integral. So let's say I have an integral or any expectation. I don't know what this expectation is or that integral is. Okay, so that's the place I'm starting from. I have an expectation and I don't know what that expectation is. But that expectation is of some function with respect to a distribution, right? So here it's the identity function or just expectation of x, where x is coming from distribution f. Now I can think that, okay, once I have that, if I can get MCMC samples from f, then I can just take an average of those samples and that will converge to this expected value by the law of large numbers. Now in missing value imputation, that's pretty much what we do. We have an expected value of the missing values as a function of some data distribution or some model, right? What is the expectation of the missing data given the other data distribution? If you can then draw MCMC samples from that, you can take an average of that, of whatever is the function inside that expectation. That would be the way I would think about how MCMC would be useful in that application.
Yeah.
Hope that's clear, Shujo.
Thank you. Yeah. Thank you, madam. Anyone else? Okay, if it is not to anyone, then I have some query regarding that. Yeah, there's some also.
Yeah,
Could
sure.
you please suggest some book and author? Uh,
The references, right?
okay, yeah.
I'm sorry, I'm not. Oh, okay. Sorry, there's another question. Could you please suggest some book or any resources for that? So I did suggest one book. I'll be honest that this is a struggle, and I'm really coaxing a couple of experts I know to write the book that everybody wants to write. I'm hoping within the next 5 years there'll be a very robust reference. But honestly, this is the first chapter of the Handbook of Markov Chain Monte Carlo is one of the best chapters, one of the best documents written on introduction to MCMC. And then the handbook basically goes into different aspects of MCMC and how it is used in various applications. So this would be, it's a pretty reasonable reference, I think, even for undergraduates who are a little bit theoretically inclined. Without theory, it's very difficult to do MCMC, but you don't have to know it very, very well, but a little bit theoretically inclined, I think it should be a palatable reference.
Okay.
Okay.
Thank you. Anyone else? If it is not, then just may I ask some just a little bit question, madam?
Yeah.
When there's during that red and blue circle, that dot in the circle, the box, how the measurement of the box it has been depended, because when the box is large, then the incorporation of the red is much more, maybe the higher. But when the box is very small, then the incorporation of the red dots will be smaller. And as it's
Yeah.
moving, I'm showing that it's going to the randomly to the nearest of that point, nearest, like the nearest neighbor, and moving
Yeah.
on that. So
Hmm.
that box has been measured, how the what is the length of the box, and how it has been proposed.
Absolutely. So this is exactly what are some practical questions in MCMC. So first, I will say that as long as the box is a box of positive area, the theoretical methodology is still sound, which means that it will still yield a Markov chain that is ergodic. So as long as the box is not a dot, okay, whatever, no matter how big it is, no matter how small it is, it will theoretically still be a valid F-ergodic Markov chain. But not all, when I say something converges to F as t goes to infinity, it means it converges at infinity, right? Now, whether infinity actually happens relatively soon or relatively later are questions that are important. If we make this box too big, like very, very big, what's going to happen is most of the dots are going to be proposed outside the circle. When something is proposed outside, it will be rejected. And when it is rejected, then I don't move. I stay where I am. So now I will continue staying where I am for a long amount of time, which means that that's not helping the convergence to my actual distribution I want to go to, because I haven't made any moves yet. Okay, that's going to be bad. On the other hand, if my box is very small, just like you've pointed out, if it's much smaller than this, then what's going to happen is I'm going to be moving very, 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 very slowly like this. Right now I'm moving like this, like in a slightly bigger window. If it's very small, I'm going to be moving very, 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 very slowly. And that will increase my correlation in the samples. If my correlations are large, then FT will converge to F in a slower rate, because every subsequent sample is not giving me so much new information also. Okay, so the trade-off is what one needs to balance. And actually, like I said, this is how do you tune this box and tune in other target distributions? How do you tune the proposal? Is a very active area of research, and it's been a very active area for the last 15 years, and there's no end to those questions almost.
Okay, thank you, madam. So like that, it's need some optimal space or optimal place. So that's why it can moving quick convergence with a limited time, and it will goes to the ultimate the
Exactly.
distribution with lesser iteration with
Exactly.
time like that. Okay, okay. Thank you, madam.
Exactly. Of course.
Yeah. Any more questions? Okay. If it is not, then on behalf of the Calcutta Statistical Association, I, Samrat Hor, from Department of Statistics, Tripura University. Uh, Thank you, madam, for your nice presentation, and it's very helpful students, not only the students, scholars, it's also for the uh, researchers, the junior researchers like us. Thank you, madam, for your nice presentation. It's much more informative like that. Thank you.
Thank you
Thank
so
you,
much.
audience,
Thank you so
for your.
much. It was lovely. Thank you so much for having me.
Thank you, madam. So now, on behalf of CSA, I am. Hello, am I audible?
Yes. Yes, you're audible. I can hear you. Yes, please.
Sorry. Thank you on behalf of the CSA, and I am going to the ending the session. Thank you, madam, for your nice presentation. Thank you all. Have a good.
Thank you so much. Have a
Good.
good night, everybody. Bye-bye.